All right, guys, sorry I missed class today. We got a quick lesson on something called Hess's law of heat summation. I think that this will be fairly pain-free. So we've been measuring in class the change in enthalpy, the energy movements of different things that happen, and we've done some physical processes like melting ice. We've done some chemical processes like burning cheese balls and things like that. So we have found that you can use a calorimeter, whether it's a bomb calorimeter or just a foam cup calorimeter, and you can measure the change in enthalpy for some of these reactions. But Hess's law gives us a way to calculate a change in enthalpy for a process rather than having to do it in a laboratory. That is, if we've done enough work in the laboratory up to the point that we can use it. So you'll see what I mean here in a second. Okay, so suppose we had this chemical reaction where we had carbon and oxygen reacting to make carbon monoxide, and we are curious what's going to be the change in enthalpy for this reaction. You could try and run this reaction using a calorimeter. In this case, probably want to use some kind of bomb calorimeter or something. It would be challenging because you'd have to restrict oxygen, and it could be a little bit of a problem. And so this would be a good example of a reaction that might be nice if we could calculate the enthalpy change without having to actually measure it in a laboratory. So what you need to do in order to use Hess's law is you have to find some other reactions that are similar to the reaction in question that we do know the change in enthalpy for. So down here below, I've got carbon monoxide and oxygen makes carbon dioxide. Turns out that's an exothermic reaction with a change of 566 kilojoules for every mole. Then I have this other one where if you burn carbon and oxygen, just like up here, if you give it enough oxygen, it'll actually make carbon dioxide. And the change in enthalpy for that one is negative 393.5 kilojoules per mole. So neither of these reactions is the same as this one up here, but they contain the same compounds as the reaction in question. So what we're going to do is we're going to use them, we're going to manipulate them, and try to use them to calculate the change in enthalpy for this reaction we're wondering about. Okay, so here's what we're going to do. We're going to either flip equations around, or we're going to multiply them by coefficients in order to make this work. Okay, so as I look at this reaction up here, we can see that we have got carbon monoxide is a product of this reaction. As I come down here, in both of these reactions, carbon dioxide is the product. So the first thing I'm going to do is I'm going to find this carbon monoxide here and decide that I need this to be on the right side of the arrow. I need to flip the reaction. So I'm going to flip it, and we're going to use some really cheesy old PowerPoint graphics here in order to flip that around. Wow, that's pretty impressive. And when it comes out, now all it is, I just turned that reaction around. What was the products is now the reactant, carbon dioxide over here. And we make carbon monoxide, 2 of them, and oxygen. The other thing you're going to notice is because I flipped the reaction so that it's running the opposite way, the change in enthalpy, the sign has to be flipped as well. And I guess that kind of makes intuitive sense that if you run an exothermic reaction backward, it would be endothermic. So then we have got the second reaction down here where we've got carbon and oxygen makes carbon dioxide. And now in my reaction that I'm interested in determining the change in enthalpy for, there's actually 2 carbons. So I'm going to multiply the second reaction, multiply everything by 2. So basically put 2 in front of all of those, multiply all the coefficients by 2. Now it was 1, 1, and 1, so now it becomes 2, 2, and 2. I also multiply the change in enthalpy by 2 because we're basically running that same reaction, just running it twice, so we get twice as much energy. Okay, and so now I'm just going to add those together. And when I do that, everything on the left side of the arrow, so that is the carbon dioxide here, the 2 of them, goes down here, 2 carbons, 2 oxygens. Those are all the reactants. Then I have my arrows, so I put an arrow here, and all the products are here. We have 2 carbon monoxides, an oxygen, and 2 carbon dioxides. There they are. And I also add together the changes in enthalpy. Okay, now what I was going for in doing this was trying to make it so that when I canceled like terms on both sides of the arrow, the 2 carbon dioxides it's a reactant and a product, so we can cross those out. And as you look at it, I've got an oxygen here and 2 oxygens over here, so I can get rid of one of these. And what I'm left with then is the reaction in question. 2 carbons and an oxygen molecule make 2 carbon monoxides. The change in enthalpy will be negative 221 kilojoules for every mole that you run that reaction. Okay, so the key is to try and manipulate the other reactions so that when you cross out like terms, it ends up yielding the reaction in question. Okay, so there's our final answer there. Here's the reaction, and that's its change in enthalpy. Let's try this a couple more times before I let you go. So we have this reaction right here. Sulfur and oxygen make sulfur trioxide. What's the change in enthalpy? Well, we've got these other related ones here. In looking at this first, I can see that there's sulfur here and there's sulfur here. They're both on the left side, so you don't have to flip it, but I do have two of them here, so I'm going to multiply that first reaction by 2. So I can just cross it out here. Now it's 2 sulfurs and 2 oxygens, 2 sulfur dioxides, and the enthalpy change is doubled. Okay. Then the other thing I'm noticing here is sulfur trioxide as a product. I have sulfur trioxide in this reaction, but it's a reactant, so we're going to flip that one. Cross that one out. Now this reaction is flipped, so that sulfur trioxide is a product, and it looks like if I'm careful and add these together, I'll get my reaction in question. Okay, so the 2 sulfur dioxides here cancel the 2 sulfur dioxides there, 2 oxygens and another one make me 3 oxygens, 2 sulfurs and 2 sulfur trioxides. You get it? Let's do one more just to make sure that we got an idea how this is going to go. So we've looked at this reaction before. This is hydrogen peroxide. It falls apart into water and oxygen. What's the change in enthalpy for that? Well, if you burn hydrogen and oxygen and make liquid water, that's a very exothermic reaction. If you use hydrogen and oxygen to make hydrogen peroxide, apparently that's exothermic as well. And so as we look at this, I need hydrogen peroxide to be on the left side. So the only place I even have hydrogen peroxide here is right there. It's a product of the second reaction. So we're going to flip the second reaction to make hydrogen peroxide on the reactant side. And then in addition, I need 2 hydrogen peroxide. So after I flip it, I'm then going to multiply it by 2. And now I've got 2 hydrogens on the left, 2 hydrogens on the right. Those will cancel. Got an oxygen. It's going to cancel one of those oxygens. We'll have 1 oxygen on the right, and then the 2 waters. That's it. Got it. So 2 hydrogen peroxides make 2 waters and an oxygen. The change in enthalpy for that will be the sum of these two, which is negative 196 kilojoules. I hope that's a good enough explanation for you to get your homework done. Again, sorry I missed class today, but we will clean this up and we're going to do a lab trying to use this idea tomorrow. Thanks, guys. Have a good